the same, it's just that how much, what is the direction in which you're changing. Now, another thing that you want to understand, and again, this may be, I'm sort of trying to, there's this statement, I think I may have mentioned that all happy families are alive, every unhappy family is unhappy in its own different way. Did I mention this? Tolstoy, Anna Karenina, okay? So everybody who gets it the same way. People who get confused in a million different ways. So what I'm trying to do is at least pick some of the million different ways and then say this is one way you may get confused and don't get confused. So here is one thing, which is if you think in terms of individual weights, it looks as if all you are changing is the magnitude by which the individual weight is changing. Just the magnitude by which the individual weight is changing. Previously it was changing, let's say 0.1, with the G in it's changing maybe 0.1235 or something. But should there be a direction in which we are going towards the minimum? Yes, there is a direction. The way you get the direction is changing individual. So if I'm going equal time, equal steps in X and Y directions, and I'm going in this direction. If I'm going half in X direction and twice in Y direction, I'm going more like that. It's pretty obvious, right? If you think about it. So changing individual weights in different ways changes the direction in which you are going towards the minimum, which is essentially what gradient descent is really trying to get. So in fact, if you think of this as a vector equation, where the weight vector is the weight vector plus alpha times the gradient. Gradient itself is a vector. Then it looks much more interesting because the direction matters essentially. But you're doing it individual weight updates and that changes the direction. Yes, sir?
So you said that you can represent it for vectors. Is there a way that you can represent these as, especially the sums, as matrix multiplication to like?
Well, yeah, those are all different issues. Yes, I mean, in fact, we are not even gotten up to that part of. Okay, so the last functions, you have this one last function we looked at. I want you to at least say that, I want you to realize that just as there are many different thresholding functions, there can also be many different loss functions. In particular, we already knew that instead of square, you could have actually minimized the absolute value, f hat of x minus f of x. We didn't do that because that would not be continuous, it's more painful. You could minimize, for example, you could also have minimized, power 4, for example, or cubic, whichever you want to minimize, depending on, and last function to some extent depends on what is your application. Okay. One of the issues is how does loss function change for classification? In the previous slide, we essentially acted as if loss function for classification is also just the mean square error. But I also said that if you're thinking of logistic threshold, in essence, you can actually say that what a classifier is supposed to do is either tell, given an input, what its class is, or give the probability distribution of this input over the classes. So the probability that this input belongs to class 1, class 2, class 3, class 4. That will be a probability distribution. It's a discrete distribution. You see what I'm saying? Now, because you have labeled data, if you have data for which you know the classes up front, so the true distribution would be 0, 0, 0, 1, 0, 0, 0 time. That means it will have 1 in one place and 0, 0 everywhere else. How many of you understand this? It's a probability distribution, and if you happen to know exactly what class it is, it's basically a degenerate probability distribution 0, 0, 0, 1, 0, 0, 0. When the learner predicts the probability distribution, it doesn't have to be 0, 0, 0, 1, 0, 0, 0. It could actually be some probability distribution where the true class hopefully is given higher probability and all the other classes are given lower probability. In fact, this is why for those of you who played around or heard of ImageNet, you would say, they talk about the top 5 classifications. So shown an example, it say, these are the top 5 labels for this. It's most likely a dog. If not, it's like a chimpanzee. If not, it is like a kid on a bicycle. If not, it's like a zebra. Okay, and then there are different probabilities. And you hope that dog is given a higher probability if you gave input as well. Okay? If you do that, then essentially the output is a probability distribution and the true output is another probability distribution. And you then need to compare two probability distributions. Two numbers you know how to compare. You know, you take the division, take the difference and square it. For probability distributions, what do? It turns out that there is this idea called mutual or cross entropy. Okay? Cross entropy essentially is basically defined this way. Imagine T, suppose this is the binary classification problem, and then you have class 1 and class 0. And T, the true distribution basically says it's 1 class 2, so actually class 1 and 0. So one probability, the input is actually corresponds to class 1, and so the probability that it corresponds to class 2 is 0. And your network Q, network came up with a probability distribution Q, that said this is 0.7, that means this is 0.2. So how do I differentiate this probability distribution from this distribution? These are two vectors. You can do some sort of a vector difference. For example, when was the last time we considered difference between vectors? Yeah, no, in this class we considered difference between vectors.
Temporal difference.
What?
Before differentiation.
No, we lived before differentiation. Yes, I mean before neural networks. When was the last time we considered difference between vectors?
Two policies.
Warner. Okay. Max norm distance between two vectors. There was a value vector in iteration 1, value vector in iteration 2. The difference, you would say that you would stop iterating if the value vectors are basically converged. To do that, you take the difference between two vectors and you computed the difference as a max norm, which is the one coefficient, one dimension where the difference is the maximum. And you drove that down to 0. Probability distributions can be thought of as unit vectors. Right? They're all unit vectors in different directions. So you can essentially compute the differences in these, and there are different ways of computing distances between vectors. For example, somebody was talking about cosine theta distance. If those of you have done anything with information retrieval, you would have seen dot product between two vectors can be seen as its distance. Okay? Two vectors are the same, their dot product, two unit vectors are in the same direction, their dot product would be 1. If they are perpendicular, their dot product would be 0. So that's kind of a distance metric. Again, remember we talked about distance metrics and what good properties they should have. All of these have those good properties. One specific other one which actually works for probabilities, and we will see this more when we get to decision trees, is cross entropy. And cross entropy comes from information theory. Okay, very impressive lineage. All that does is it says the cross entropy is defined as minus T of 1 log of Q of 1 minus T of 2 log of Q of 2. Now P of 1 is 1, Q of 1 is 0.7. And then T of 2 is 0, Q of 2 is 0.9. So this will be 1 times log of 0.7, negative. That would be the cross entropy lastly. And you can essentially show that the cross entropy is highest when P and Q are the same. I'm sorry, cross entropy is lowest where P and Q are the same. So imagine Q1 is 1 and 0. Right? So then it would be T of 1, which is 1, Q of 1, which is 1, log of 1 is, what is log of 1, guys?
0.
So cross entropy will be 0. So cross entropy between two distributions will be 0 when the distributions are exactly the same. Otherwise it will be a bigger number. So then you take the average cross entropy over all the errors for each example. You are saying, oh, this is 0.7 dark, 0.7 dark, so 0.3 not dark. This one is 0.9 dark, 0.3, 0.1 not dark. This one is 0.5 dark, 0.5 not dark. And for each of these labels, you actually know what their true distribution is. 1, 0 here, 0, 1 here, 0, 1 here, etc. So then I can compute the cross entropy for each of the examples, take the average or the sum, drive it down. That is very strange way of reducing error. It looks like you are much happier with driving down the mean squared error because you kind of know that. But if you think of this as probability, the right error to drive down would be cross entropy. If you do cross entropy drive down, then you will essentially have in this error function now will be in the sum pi log qi type. And so it has logarithms inside the error function. So you need to remember that the log of x, differential of log of x is? Yeah, that's great. Okay. So you have to use that. Okay, so if you do this, then you would call cross entropy loss, also people call it log loss. Remember I mentioned logistic regression? Logistic regression is exactly this. Except instead of minimizing the mean squared error, you minimize cross entropy loss. Then that is basically logistic regression. And logistic regression is one of the latest first ideas that you should try if you're doing classification. It's basically linear sum of features, but you throw it up into e power, linear sum of features. E power minus linear sum of features. 1 by 1 plus e power minus x is the sigmoid function. Again, what I'm trying to do is essentially build them in little pieces, because if you show the whole thing and show the full thing's derivative, it looks complicated. But essentially, you can change any of these pieces, and your chain rule, which is your greatest friend, will help you figure out what the gradient is and how to make the step in the right direction. Okay? One other thing, and before we actually go on to some fun stuff on TensorFlow, is this is something else that you want to remember. When you're trying to do learning, you've been given a bunch of data. That whole thing is a bunch of data, that set of data. And you call the data labeled data. In supervised learning, basically, which is what we are looking at, the word supervised means that for the training data, the teacher has told you what the answer is. Okay? And in the value function case, the teacher for you was what, by the way? When you were doing the value function learning, who was the teacher? Temporal difference learning was the teacher for the value function learning. Because that told you how much to change yourself to be close to your neighbor. Okay, so it told you for each state what is the value each state should be in the current iteration. And then you use that to modify the weights such that you come closer to what is expected of you. Okay, so supervised learning comes with labeled samples. Typically, by the way, most people, even though we came into supervised learning through regression, if you walk out of this class and ask people, what do you know about learning, they will think classification. Because it looks as if all you are interested in is it a dog or is it a cat? That's sort of, is this a fraudulent credit card transaction or not? Is this person a terrorist or not? This is the kind of stuff that we are into. And so those all become classification learning theory. And all I'm telling you is classification and regression have the same theory behind it all. The difference is the function is in one case, real value function, could be nonlinear, but real value function. Another case, it's basically a discrete function. Okay, so now if I start with some data and I know the labels, that means I know for each of the pictures, this is a dog, this is a cat, this is a zebra, or for each of the credit card transactions, this is the fraudulent transaction, this is normal transaction, this is fraudulent transaction. For mails, this is a spam mail, this is not a spam mail, this is a spam mail, this is not a spam mail. So that's the labels. For regression, let's say computing the final cumulative final cumulative of your course, then for each of the students I will tell what the cumulative number is. Okay, and so then that will be the regression. So those are the labels. So if I given the label data, one of the issues is you realize that you're doing learning by essentially minimizing the loss function. You're doing learning by minimizing the loss function. Right? Now the question is, you have to be careful that when your learning algorithm actually works, you don't know what it's going to be subjected to. The test data is not under your control. In real life, after you essentially train like a spam mail classifier, you would then put it on your mail system. And then it will say all mails from Rao, which are telling you when the midterm is, are put in the spam folder. And then you get screwed. Okay, and you can yell at Google. You see what I'm saying? So real life test data is not known at all, like at all. So what can you do during the training? You basically take, if you took all the data you have that has labels and just train completely on it, then you have not essentially differentiated between the training loss and the test loss. Remember training and test error that I was talking about last class, and then pointed out that training error, as you drive down the training error, test error in the beginning drives down and then starts increasing something. And you want to essentially separate that. So normal thing you do is you take, let's say there are 11,000 samples I gave you, you take 1,000 samples, put it in a Coca-Cola vault with a real key. You'll never ever touch that test data except when you're testing. It's very important. So now you only have 10,000 samples left. So then you have to use these 10,000 samples to basically come up with your best way of learning the concept. So you might basically say, after 10,000, I'll take 9,000 to train my classifier and 1,000 to validate to see where its error is. And then this validation stage can help me decide different ways of learning the classifier. So for example, I can change the error rate, I can change the number of layers in a deep neural network, I can change all sorts of things until the validation error is in the level that I feel developed. So validation error, the validation set is sort of very close to the test set. In the beginning, people tend to think there's actually only training set and test set. But I'm telling you that there are two really different kinds of test sets. One is the test set that is in the Coca-Cola vault, that you're not going to touch at all during the learning stage. Right? And then there is the validation set, which basically you do try. And the reason you have to separate this way is if clearly the training data influences the weights that you come up with, because you're directly gradient descending on the training data's labels. But even the validation data indirectly leaks into the learning. Because you keep looking at the validation error, you keep changing the way you are learning. Do you see what I'm saying? The true test is, the world doesn't say, I know by the way, a test is like this. Nobody says that. You keep asking me, what does the midterm look like? As if somehow I'll say something and I'll actually be responsible for what I said. Okay? Midterm looks like midterm. You see what I'm saying? And how do you train for the midterm? You essentially can just take all the homework problems that have been done, take them all as they are training data, because I told you how to do them. Use them as training data, memorize them. And then you come to the midterm, and of course if one of those questions come, you do, otherwise you get done extremely fast. Right? The other better idea is you take the homework problems, right? Take, let's say, 90% of them, try to understand, try to actually kind of more or less almost memorize and understand exactly how the solution came up. And then test your understanding on the 10% of the problems that you kept away. That's how you validate it. You see what I'm saying? That's how you validate it. And then, of course, of all this, you come to the midterm and it will be a total surprise, right? Because that's a test data, right? You're not supposed to know. So then we'll say, well, this person learned well because they did well on the midterm. This person didn't learn well because they didn't do well on the midterm. There's a lot of connection between your life and this learning that's going on here. Okay. Okay. So that's about training, validation, test losses. And then, in fact, there is a slightly better idea called k-fold validation. K-fold cross validation just for the validation part. That means you take this part of the data and split it into k splits. And then you can try, let's say k equal to 10 splits. You can do 9 of them as a training and 1 of them as a test. Again, it's a practical thing and it's important. Okay. Again, who was the person who was asking, where's the theory for this whole damn thing? They left. They gave up and left. So the point is actually one of the beautiful things about this is that there is a theory for learning called PAC theory. And it's as wishy-washy as it can get. PAC basically means probably, approximately, correct. Okay? Learning cannot be proved to be right. Probably, approximately correct basically assumes that if the training and test data were taken from the same distribution, then a good learning algorithm will probably approximately classify the test samples with high accuracy. When do you eventually say that the midterm, which eventually is next week, I'm sure Wednesday around this time, there will be a large number of unhappy people. It's just the way the exam would be. And all exams are unfair. Because if you didn't do well, they're unfair. Right? But when is it truly unfair exam? Imagine I set 2 different midterms, okay? Midterm 1, really hard problems from MDP and reinforcement learning. Midterm 2, only problems from multi-layer neural networks. Which is an unfair exam? Which is more unfair? The multi-layer neural network. Because I told you the training, you don't have to think about it at all. So your entire training data was MDP and reinforcement learning and A-star search and and min-max. Then you come to the exam, it's like this Monty Python, now for something completely different. Let me do neural networks. Or, for example, the training problems had like 90% of them are about things other than reinforcement learning and 10% are from reinforcement learning. Test has 90% of the problems from reinforcement learning, 10% of the problems from non-reinforcement learning. This is when you get onto ratemyprofessor.com. Not the other test. This is when you say that test is unfair. Otherwise, you're just whining. Right? Basically, I asked the questions in the same distribution as what you have trained on, and you blanked out. Don't yell at me. You see what I'm saying? So that's where the theory comes from for learning, which is probably approximately correct. Okay, what I'm going to do now is show some of these. Show some of these in the. In the TensorFlow, and then when we come back next class, we will basically, so TensorFlow will take us from sort of seeing these things work in perceptrons and multi-layer perceptrons, and then next class we'll start talking about multi-layer perceptrons and talk as much practical stuff about deep networks as possible. I'm hoping still, fingers crossed, to at least tell you something about convolutional networks, which is basically the big thing that everybody talks about for years. So that's my class. So let me do this one part. Okay, so how many of you actually played with this? So the rest of you don't have any curiosity whatsoever in life? I mean, I showed you this thing exists. Okay, so. Okay. one hidden layer and so and then we start. Okay, so let's start. I'm basically getting you to a point where you will spend time when you go home, compulsively playing with TensorFlow to get a better idea of how some learning works on at least nice visualizations. Okay, so this is just mostly visualization. So imagine I have, and most of the examples here are classification examples because that's it's easier to see the connections. Okay, but again, remember classification is just a discrete output, version of equation. Okay, so I have, let's say, this particular data. This data is of two classes. This is training data. This is test data. Sorry, this is training data. Some of is blue class. Some of this is orange class. And I'm trying to given a new data point from the orange class. This guy should be able to tell that it's orange class. That's basically the idea. And so what I do is, and if you notice there is a number called epoch here, and there is a learning rate, that's the algorithm. You can play with that. You can make it big numbers and see what happens, small numbers and see what happens. This is activation. This is basically, if you see the activation, there is ReLU, we talked about, tanh, hypertangent function, sigmoid, and then linear. Linear activation means no activation at all. Okay, let's start with linear first. Okay, basically linear perception. Okay, and then regularization, don't think about it right now. And then forget. And then problem type can be classification arbitration. I just pick classification. Okay. So I have x1 and x2, and then I try to run. And here there are two numbers being shown: test loss and the training loss. The training loss is how well does the machine think it is classifying the training data itself with respect to whatever it is it learned. And the test loss is how well is it doing with respect to the test data that was not shown to it. It was only shown later. Okay? And so you notice, of course, that, by the way, so you notice that this was learned perfectly. And you know that it's learned perfectly because test loss is 0, training loss is 0. Right? Very nice. Okay. And then, so here x1 and x2, of course, each of these points have x1, x2 coordinates. And basically, it's not surprising what you might have thought of, which is essentially there's some sort of a separation between these classes. In fact, one good way of thinking about the classification functions is as decision surfaces. So they take the space and put hyperplanes. And say above this hyperplane it's one class, below this hyperplane is another class, between these two hyperplanes it's a different class, and so on. Okay? That's a reasonable way of thinking about discrete valued functions. Okay, discrete valued range functions. Okay, so that's what you did in this particular case, and that's fine. So you can try, let's say, sigmoid, and then do that. And notice that the training is slightly different. The speed will be slightly different, but it too learned it. Okay? So that's fine, that's good enough. Now I want to try that. Okay? Now, from the point of view of these hyperplanes that I told you about, you can imagine how to draw hyperplanes. I mean, presumably, you basically are looking at the training data like this. I think you say, and then this quadrant is orange, this quadrant is blue. The second and fourth quadrants are orange, and first and third quadrants are blue. That's what is the concept here. When you're looking at the individual points, you are obviously missing the forest for the trees. But if you look at the entire space, this is basically what you can see, right? So the question is, what does perceptron do? Okay? So I basically start doing this, and all of a sudden things aren't looking all that good. Now, part of what happens is, so essentially it did do reasonably. So notice this. It somehow essentially found training loss much lower, but test loss remained at about 40%, at 0.7. So that's the difference. The best learning algorithms, training and test loss track each other. If the training loss is reducing and the test loss is not reducing at the same rate, then there is overfitting going on. Okay? Anyway, so in this particular case, this, by the way, is what Minsky, Papert were essentially jumping up on. They essentially said, guys, instead of just using tensor playground and then running various things and hoping for the best, you can ask, was the original problem such that it is linearly separable? That means, can you draw a line in the 2 dimensions? Can you draw a line such that on one side of the line are all the one class, other side is the other class? This is a binary classification, 2-dimensional data. Can you draw a line? And if it is a multi-dimensional data, can you draw a hyperplane? Right? Okay. So, is this separated? Obviously not, right? You couldn't separate it. Now, here is an interesting question. So, there are things here. This is x1 and x2, but apparently I can also give an input called x1 square. And I can also give an input called x2 square. I can also give an input called x1, x2. I can also give an input called sin x1 and sin x2. You feel really mathematical at this point, right? So instead of just taking x and y, think of these are the features. Remember, instead of states, we went from states to features. These are the features somehow I extracted from the state. Why did I extract those? We don't know. But let's say I tried this. What do you think will happen in this case? If I try to do this now basically it's still the same perceptron. It's the same perceptron, except it has a lot more inputs. All the inputs are derived from the original inputs. So there is no extra information being asked from the teacher. What will happen now? If I do this, done. The same problem with more features, done. So first of all, there is a theorem. I believe it's called a Maxwell's theorem or something. A theorem basically says, irrespective of the data, let's say in k dimensions, you can blow up the data into k plus big N dimensions, where N is a huge number. So you make the data be higher dimensional than what you've been given. Remember, you were given, in this case, 2-dimensional data, x1, x2. But you convert it into 1, 2, 3, 4, 5, 6, 7-dimensional data. Those of you who have any background at all in learning think this is such a bozo thing to do. We talk about dimensionality reduction, never dimensionality increase. But if you actually increase the dimensions with sufficient number of dimensions, all data is linearly separable. With sufficient number of dimensions, all data is linearly separable. You know what?